Hello, in today's video we are going to take up a question from the chapter of fluid mechanics. And when I say fluid mechanics, this term fluid mechanics itself is a hint for the question. Otherwise, the question is quite deceptive and you need to understand each and every phrase in the question very carefully. So, let us have a look at today's question. The question goes like this. A cylindrical vessel of inside radius capital R, 30 mm, is filled with water. Another empty cylindrical vessel of radius small r, that is 25 mm, and with an insignificantly small mass, I stressed on this, is coaxially pressed into the bigger cylinder so that length of the part in the water is 300 mm. See the diagram. If it is not clear, I am drawing it again so as to explain this. This is a cylinder of radius 30 mm, capital R. Some water is inside it. Now you take another empty cylinder. This empty cylinder having slightly smaller radius. There is some water here. Now take this empty cylinder and push it into water. So naturally you will see something like this. Both the cylinders are open at the top. Water will fill up this bigger cylinder like this. So this is empty. There is nothing over here. I mean, there is air. So the question says radius of this smaller cylinder is small r, radius of this bigger cylinder is capital R, and length of the smaller cylinder, that is inside water is 300 mm, that is capital L. Now you are holding this smaller cylinder, you release it. The moment you release it, a very short while after you release it, what will be acceleration of the smaller cylinder? That is the question. Find the acceleration of the inner cylinder right after when it is let free. You do not have to account for surface tension and viscosity of water. That means ignore surface tension as well as viscosity. Give it a try, and again I stress upon the fact, read each and every phrase in the question very carefully. Here I proceed with my solution. The first and foremost thing that is of great importance is that this inner cylinder has insignificant mass, massless. It does not have any mass. So otherwise, I was getting tempted to somehow use this equation because the question is asking about acceleration. When I release it, what is its acceleration? So I could have found the value of acceleration had I known the mass of this cylinder, maybe. If mass was a finite quantity, I might have tried to find force acting on this cylinder, and using that, I might have calculated acceleration. But this route is basically closed because mass is tending to 0. So for any finite force acting on this cylinder, the acceleration would become infinite. What does it mean? Haha, there is a big hint, right? Yeah, okay, I'll come to it later on. But this route doesn't seem meaningful. Though this equation will be useful, I think. Let us see. Then I said that there is a big hint that this is a question of fluid mechanics. Okay. So it is a question of fluid mechanics. And in fluid mechanics, what do you study? You study buoyancy, Bernoulli's equation, continuity equation, things like that. So those are things which are going to be applied here to solve the problem. If this is enough of a hint, do give it a try again. Here I am proceeding with my solution. Look at this situation. This big cylinder was having some water. This small cylinder is pushed inside it. Now the situation looks like this. You release it. A short while after you release it, what is speed of this cylinder? Almost 0. When you release a ball, what is speed immediately after the release? Almost 0, tending to 0, But what is its acceleration? It is not 0. So if a particle is at rest at a particular instant, it does not mean that its acceleration is also 0 at that instant. तो जैसे ही आपने इस इनर सिलेंडर को छोड़ा, what is its speed? Almost 0, okay. But what is its acceleration? It could be a finite number. So speed tending to 0 does not imply that acceleration is also 0, right? So as soon as you leave the inner cylinder, its speed is nearly 0. I am saying nearly 0 because a short while after you release it, it will have some speed, but it is negligible. You release it and we are measuring its speed after 0.0001 second. So, okay, it will have some speed, but it is tending to 0 only. Now the second thing. So immediately after the release, this cylinder is having 0 speed. Okay, fine. So these points, I mean the floor of the cylinder is moving with negligible speed. Okay, fine. Speed 0 does not imply that acceleration is also 0. That's also fine. Now, if I ask you, how much force the water is applying on this inner cylinder, do you have an answer? Yes. The inner cylinder is massless, and as I pointed out, if it is massless, then F is equal to ma tells you that F is always 0 or nearly 0. So net force on this cylinder must be 0. It is massless. A massless object cannot have any finite force acting on it. So from here, it is open to atmosphere. Atmospheric pressure is acting on this cylinder. This tells me that this water must be applying atmospheric pressure from below onto this cylinder. The force due to atmospheric air and force due to water must balance out. This is massless cylinder. Here the forces are all horizontal. We need not worry about them. They will cancel out. So what does it tell me? It tells me that pressure right here, just below the cylinder, is P naught, atmospheric pressure. Here the pressure is atmospheric pressure. Here also the pressure is atmospheric pressure. And it is commonsensical also. Like the atmospheric pressure is exerting some force over here. The cylinder itself is weightless. So सिलेंडर है या नहीं है क्या फर्क पड़ता है, यहाँ जो प्रेशर है वही यहाँ प्रेशर है. तो नेचुरल सी बात है, नीचे में सिलेंडर के फ्लोर के जस्ट नीचे पानी का जो प्रेशर है वो कितना है, पी नॉट के इक्वल है. देयर इज वन कंक्लूजन, देयर इज नो फोर्स ऑन सिलेंडर, इट्स स्पीड इज ऑलमोस्ट टेंडिंग टू 0, but it is having some acceleration that we are supposed to find. Now as you release it, what will happen? Water pushes it, it is pushing it, and here water is at higher height. So this water falls down and this surface, it's not surface actually, but this water level begins to rise. I mean the cylinder begins to rise. This is what will happen. So let us assume, we can use this diagram also. Let us assume that after some time, this length, let me denote it by y. And let us say the cylinder has moved by a very small distance x from its initial position. You released it from here, it has just gone up by x, and right now this height is y. X is a very small number, almost tending to 0. So the speed of the cylinder is nothing but dx by dt, right, which we are saying is very small. And this water surface is falling down at a speed v, which is minus dy by dt. Why I have written minus? Because y is decreasing, right? So minus dy by dt. Actually, if y is, just a minute, if y is this height, then minus dy by dt is v plus u. U is speed of the floor of the cylinder and v is the speed of the water surface here. अगर ये 3 मीटर पर सेकंड है, 1 मीटर पर सेकंड है, 1 मिनट मान लो ऐसा, ये बहुत कम है, 0.01 है, ये 3 है, ये 0.01 है. तो एक्चुअली में जो y डिक्रीज हो रहा है, इट इज डिक्रीजिंग एट ए रेट ऑफ 3.01, बट 3 plus 0.01. Okay, let it be 3 only. So minus dy by dt, rate at which y is decreasing, can be approximately written as v only. We need not write v plus u because u is very small. The cylinder has been released just now. So its speed definitely is tending to 0. This is what we are saying. So v is equal to minus dy by dt. Okay, that's fine. Now just have a look at the cross section of this container from the top. How does it look like? It will look like this. This is inner radius r, this is outer radius r, and water is here, in this annular space. Let us apply equation of continuity. Actually, it is a case of flow of fluid only. Streamlines are going like this. Don't you think so? Water surface is moving down, streamlines are going like this. If possible, try to draw a rough sketch of streamlines. Here the speed is negligible and here speed is substantial. And density of streamlines represent speed of flow. So keeping that in mind, you can draw streamlines also. I am not doing that for you. Give it a try. But it is a case of flow of water only. Fluid in this narrow channel is going down and it is going up like this. It is a situation very similar to a fluid flowing through a narrow pipe which suddenly gets widened. Yes, fluid is flowing in this narrow channel, it is going down and all of a sudden the channel widens, it is going up here. It is something like that only. Okay, you just need to understand that here we have some velocity which is not exactly tending to 0. Fluid is moving down, but here the speed is almost 0. Almost 0 in the sense that this speed is small compared to this speed. Let me directly apply Bernoulli's equation between this point and this point. Let this be reference level. What is pressure here? P naught, atmospheric pressure. What is speed there? V, rho is the density of water. If I take this as a reference level, what is height here? Y. Now what is pressure here? As explained earlier, it is still atmospheric pressure. What is speed? Half rho u square. And what is height? 0. And this is what I am repeatedly saying, that half rho u square is a quantity which is extremely small compared to half rho v square. If this is 3 meter per second and this is 0.01, in fact you can write exact relationship between these two quantities. We will do it in a short while, but just to make you understand, this number is large compared to this number. So square of u is even smaller than square of v. So it makes a lot of sense to take this as 0. P naught cancels out, and what you are left with is v square by 2 is minus rho g, g into y, I am sorry. If you differentiate this with time, it becomes v dv by dt is equal to minus g dy by dt. Now what is minus dy by dt? That is v. So minus dy by dt is v, therefore dv by dt. Wow. dv by dt is g. Oh. So liquid here is falling at acceleration g. It was commonsensical. Think for a moment. Yes, I forgot to tell you one more thing. If speed here is v, here also it 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 is v. There is a narrow channel. An equation of continuity says speed has to be same everywhere. The most important thing that we have discovered just now, water is just falling freely. Weight of this cylinder is negligible. It is putting no resistance to movement of water. So acceleration g makes a lot of sense. So acceleration of surface of water, acceleration of each and every particle here is g. Is it? Yes. But this was not the question. Question asked me to find acceleration of the cylinder. So, I need one more relation which can tell me what will be acceleration of this surface or water over here when acceleration here is known, and that can be done using continuity equation. Continuity equation. Again, let us assume that this is going up with speed u and this is falling down with speed v. So, A1 V1 when I say this is A, this is area of cross section into speed v. So, I can write pi r square minus r square into v, A1 V1 is equal to A2 V2. What is A2 V2? In this case, this is A2, pi small r square. V2 means u. So, pi small r square into basically u. Okay, u is very small compared to v. In fact, this is the exact relationship. Pi cancels out. Capital R is 30, small r is 25. You can work out the value of u in terms of v. So, u is sufficiently small compared to v. That is what I am saying. You have released the cylinder. A very short while after that, the cylinder is going up with some speed u, which is almost 0. That is what we have taken, at least for writing this equation, which was sensible decision, because even if u is finite, it is a small number, its square is going to be very small. So, let us agree to disregard that. In front of v square. So, this is what we did. And now you differentiate this. So, you get this du by dt. So, you are looking to find du by dt. You know the value of dv by dt. You have just calculated that dv by dt is g. In fact, no calculation was required for dv by dt. If somebody could have observed it carefully, and the answer was always g, and that is what we discovered. And this is du by dt, which means acceleration with which the cylinder will go up. I hope you enjoyed the session. Think a lot more about this question, and you may start smiling when something hits you. Do it. See you in the next video.